Good afternoon. A few years ago, Gaussian, PGI, and NVIDIA embarked on a project to enable Gaussian on GPGPUs. In this talk, I will give a little bit of an idea of where we are along this project. I will start by explaining a little bit what Gaussian is vis-a-vis this project. This will help us understand what are the choice of design guidelines. Furthermore, I will talk a little bit about the parallelism model implemented by Gaussian and how we are implementing the framework. After talking where we actually are in this project, I will show some performance results. Gaussian is probably the most widely used application for computational chemistry that applies quantum theory. It's been around for a very long time, initially in the 70s. And its long life is becomes evident by looking at the wide spectrum of computational techniques, computational styles, and computational algorithms that can be found in the code. At the same time, it is a very feature-rich program. Practically, it's probably the most, it has probably the widest spectrum of features of any of the applications in this area. Gaussian is very large. While it is not a single binary, rather it's a sequence, it consists of several binaries that are linked together according to a route that is predetermined by the input that is being used. In other words, by the type of calculation being performed. However, Gaussian is very modular. In this modularity, it's expressed in several ways. Among others, code is reused not only within a binary or a link, but also among binaries themselves. This has profound implications in terms of what it means when you change the code. If you alter the code for the purpose of improving or accelerating a particular piece of the program, one has to ensure that this does not negatively affect other portions of the code. When trying to accelerate Gaussian with GPUs, we decided to adopt a model in which we use the GPU as a coprocessor. This allowed us to essentially leverage all the program that all the existing program and the algorithms already present in the code, as well as the optimizations. While looking at this graph, the CPU code denoted here is not necessarily single-threaded. It could be multi-threaded. And we try to put critical functions on the GPU that are actually apt for GPU acceleration only as a coprocessor. So when we are looking into enabling Gaussian on GPUs, one of the main concerns is to have an unified code base. This simplifies everything that has to do with maintainability of the code, but also it permits the leveraging of the existing code and algorithms. Of course, at the end of the day, the idea is to accelerate the program execution. And so we will be looking at performance, even though it's not the first goal as we are working towards the enabling of the code. So when I present the results later on, bear this in mind. We want to have a wide impact on the Gaussian user community. So we look into enabling code that is relevant to these users. But also it has to be appropriate, meaning that the code will run well on the GPU. Part of the accelerator model, or GPU as a coprocessor, is that we will try to use all the resources available to you, all the computational resources, meaning we try to use the CPUs where appropriate. The ability to do this, to obtain the quote-unquote holy grail of code unification, can only be done if we use a directives approach. And the emerging and evolving compiler technology associated with OpenACC has proven to be probably the best tool that we have today to do this. OpenACC, as I say, is evolving and as becoming certainly open in different aspects. It is open in the sense that there are several compiler vendors that are busy implementing this technology, and more are coming. And also, it has different targets, so not only NVIDIA and GPUs. The beauty of using directives to enable code is that allows you in a fairly simple and straightforward way use the high-level language, in this case Fortran, to do at least three things automatically. One, indicate a piece of the code that will be slated to run on the GPU. This is marked by beginning and end directives of, in this case, kernels. The compiler itself, in this particular case, will take care of the translation to the GPU and the launching of the GPU code, what we call the launching of the kernel. And also, it will take care automatically of all the data transfers from the CPU to the GPU that are needed. Now, here I'm also showing the if clause. That's an important clause in the context of Gaussian, because it also indicates that for the to-do loops in this kernel region, two pieces of code will be generated, one for the GPU and one for the CPU. For more details, please look at the other talks at the GTC for OpenACC. Let us understand a little bit first what Gaussian has done in terms of parallelism. Gaussian uses two levels of parallelism today on the CPUs. One, inside the node, it's shared memory parallelism, and it's based on OpenMP. And the other is between nodes, and for that it uses the Lynda environment, which is very similar to what most people would call MPI. This parallelism is hierarchical, meaning that if you have a multi-node system on which you're running Gaussian, you distribute the code, the execution first over the nodes with Lynda, and then within each node with OpenMP. So I will restrict myself to talking about what's happening inside the node. The internode parallelism should happen automatically when appropriate. Gaussian uses a less orthodox approach to managing its memory inside its shared memory parallelism. In general, when shared memory parallelism is used via, say, OpenMP, the memory footprint of the program is automatically increased when needed as more threads are used to execute the parallel region of OpenMP. In Gaussian, a different approach has been applied. We actually predetermined and pre-allocate a large piece of memory, kind of a heap, that is used back and forth as a execution progresses. When a parallel region is reached, the amount of memory between the high water mark of the sequential region to the end of the allocated memory will be subdivided by the number of threads that are going to be used in the execution. So in this slide, I'm showing an example with for OpenMP threads. When we attach, or when we are going to use GPUs, the first thing we do is to assign GPUs to some of the threads. If we have, as usual, we will have more threads than GPUs. The threads that don't have GPUs will actually execute the same kind of work that the program would do if there were no GPUs at all. Of course, if the load distribution is static, this will cause a very big memory performance bottleneck if the performance of the threads with GPUs is much different than the performance of the threads without GPUs. Fortunately, very early on, we introduced in Gaussian a dynamic load distribution mechanism that now actually takes care of this immediately. So this is a non-issue. The memory mapping happens via a sort of sliding window approach. So essentially what we do is assign or map every private piece of memory that was reserved for a thread to the respectively GPU. So in this slide, I'm showing an example of 4 threads and 2 GPUs, and the 2 first memory segments are assigned to GPU 0 and GPU 1. Using GPUs adds an additional level, or opens the possibility of using additional levels of parallelism. So we were using Lambda between nodes and OpenMP within nodes, but now within a thread, thanks to the GPU utilization, we have new avenues of simultaneous execution. First, we can overlap execution of a CPU with a GPU. This is because we launch the so-called non-blocking kernels. After GPU's launch, the CPU continues to work, and if that work is concerns data that is not needed by the CPU, this data that is not dependent on what's happening on the GPU, this can just proceed. And when the GPU is done and the CPU needs its data back, then the CPU execution will continue. But here we have a region of overlap. In NVIDIA, there is a concept of GPU streams. That means that one thread can have more than one kernel running on the GPU. At this point, we are not making use of this capability in Gaussian. Another type of overlap is that of data transfers. And I'm sure that you have heard in every GPU presentation here at the GTC that this can be one of the major performance bottlenecks when a lot of data has to be transferred, or very often data has to be transferred between CPU and GPU. So in Gaussian, we use the ability to perform these transfers asynchronously. And that means that if we know very early on what kind of data will be needed on the GPU, we can initiate the transfers so that by the time we start the GPU execution, the data is already there. Now, then comes the last and probably most important part of the GPU acceleration, and it is the power that is embedded in the GPUs the power that we try to extract via its parallelism and vectorization capabilities. Now, this is not as straightforward as one thinks, because while the data dependencies, the parallel dependencies that exist among threads for the CPUs have been resolved, that says nothing about data dependencies within a thread. And so part of the challenges to create well-performing GPU code is to resolve these data dependencies. Also, there are other data dependencies that tend to prevent us from using GPUs or slows down GPU execution, and that has to do with coding techniques that interleave gather or disk I/O operations with computational sections. So we have been busy trying to separate this, and in general, these tend also to help the CPU-only code. So how does this actually look like when we're implementing it on the code? So let me give you some examples based on some pseudocode. As I said, originally, Gaussian will call a pseudomain, with this binary, where we pre-allocated a large chunk of memory, and where we call subsequently data that are arrays that will have own names, or that will be scratch arrays. So it will look like something like this. Then we have, for example, down the calling tree, the parallel region for OpenMP, the subdivision, as we indicated, to protect certain areas that will have names when you go inside the code. You can see this here, V2 and V3, or that will be also a scratch array in itself. Conceptually, what we do then is that we would try to assign a GPU to a thread. We allocate a namespace for the device data, for the same arrays on the device, and then since we are going to be running maybe data on the GPU or data on the CPU, we actually then need to create different routines here to execute this type of code. It really becomes very messy when you start to look at how this would be implemented in, for example, CUDA Fortran, before we had OpenACC. Things will start to look something like this. We need to separate the namespace, this v1_d, and then the whole calling tree underneath work GPU and work CPU would be practically the same, except you have to add these arguments. And this is, of course, very tedious and error-prone. Using OpenACC, we now can actually unify the namespace. Just with a couple of directives, it is possible to take care of the data allocation, the data deallocation, and even the data transfer. And all the computational that happens here will be guided by, again, OpenACC directives, but the data management is taken care of. So if we go back to the original code, you see the potential benefits of using OpenACC. So today we have implemented the directed Hartree Fock and first derivatives in the default path of Gaussian for closed and open shell molecules. We have had to put some of the code still in CUDA Fortran because, as I indicated earlier, OpenACC is really standard is still being developed, and there are some features that are still being implemented, or some features with issues that need need to be corrected. When running calculations of hybrid functionals, in these cases, the Hartree-Fock part takes the bulk of the time, and so they benefit from we having attacked that portion of the code already. A very good example that we have implemented today is the triples corrections for closed and open shell molecules for default pass in MP4 and CCSDT parent CCSDT. We make extensive use of Kubla's libraries here. We also look at the CSD path of the code, so the iterative portion. And while that is today on a GPU, its performance is really not as good as we want to, and we are investigating performance issues associated with that. So when we perform a Gaussian calculation, usually you process the input, you compute the base energies, essentially say Hartree-Fock calculations, and then it's possible to do some extra calculations like first derivatives for forces of geometry optimizations, or you do high order energy calculations like MP4 or CCSDT, and then you compute molecular properties. So the Hartree-Fock calculations on the right essentially consist of two pieces. You form the Fock matrix, and then you diagonalize it to get energies and determine convergence criteria, and you do this in an iterative manner until you achieve convergence. The forming of the Fock matrix, which is done by, in a recurrent way, calculating the electron repulsion integrals that is seen here on the bottom left. This is done by picking and screening quarters of shells and then putting the data into a temporal array. This temporal array is used subsequently to gather and multiply into elements that will be scattered into the Fock matrix. Today, of the bottom part of this slide, the picking screening is still on the CPU, whereas the other three parts are running on the GPU. So, initial results. In this graph, I'm showing the speed up of DFT calculation, actually force calculation for valinomycin using a fairly large basis set. We see the speed up of the run in green using GPUs versus not using GPUs on one node of a modern Ivy Bridge-based computer. We use 20 threads without GPUs as a reference, and then 20 threads with 6 GPUs for the GPU accelerated case. The first two columns denote the total execution time from beginning to end, and then 502 is the Hartree-Fock calculation, the DirectICF. 703 is the first derivatives. Each of them is subdivided in the pure Hartree-Fock part and the XC quadrature, and in case of the 502, we have also the diagonalization. You see that the Hartree-Fock has been accelerated by close to 60%. Similarly, the 703, the Hartree-Fock part, is a little bit around 50% faster. We have not done any work on the XC quadrature. In total, we get an acceleration of around 40%, which is really not great. But as I said, this is something that we are still working on, and we think we understand which kind of things we need to attack to improve the performance. When you do a higher order high theory calculation like CCSDT, we have to go through the first steps as before. But now the CCSDT consists of an iterative CCSD, which I already indicated is not well performing at this moment. But then on the right-hand side, the triples correction, which consists essentially of a series of matrix multiplications and matrix transpositions that can be quite complex, but the matrix multiplications use an out-of-core logic, meaning that there is some I/O, disk I/O that need to be performed. Here the results are really much better, actually pretty good. Again, the total time corresponds to the total calculation, and 913 is the binary that contains this piece of code. The triples correction is accelerated by almost a factor of 17, actually probably over 17x. And here we're comparing 20 threads of the CPU versus 6 threads and 6 CPUs. Because the CCSD is not performing that well, the total acceleration is actually a little bit under 7x. But it's interesting to see that the triples correction is already faster than the CCSD iterative section. CCSD is order n to the 6th type of problem, whereas the triples are n to the 7th. So this is really very promising. So in closing, you can see that while we're seeing really very nice results, promising results for the triples calculation, still a lot of work needs to be done for the DFT and Hartree-Fock sections. We certainly need, there's room for improvement. Our goal is to deliver a product quality code when we release it to the customers. And in order to do so, we need to continue unifying the code base as OpenACC becomes becomes better. We need to tackle the non-default paths to the code, and without indicating a particular order, on our plate are working on the second derivatives, the XC quadrature, TD, DFT, etc. And performance tuning will be something that we do continuously to try to work on a code that will benefit our customers. With this, I really would like to thank you, and I think there's still some time for questions. Thank you very much.